All right, here's the last of the videos for limits. So we're still describing the continuity of these functions. Here's g of x. You got x plus 1 over x squared plus 36. Discontinuities are domain errors, usually a divide by 0 error if there's no roots involved. So you just set the bottom equal to 0 and see where, zeros are showing up in the bottom. By the way, x squared plus 36 does not equal x minus 6 times x plus 6. Okay? It also doesn't equal minus times minus. Yeah, it also doesn't equal plus times plus. This is an unfactorable polynomial. So at this point, you got no choice. It's like I can't take x plus 1. I can't factor that. X squared plus 36, can't factor that either. So x squared plus 36 equals 0. Subtract 36. X squared equals negative 36. If I square rooted both sides, I get plus or minus 6i. But we really haven't talked about how imaginary numbers factor into continuity or limits at all. So what you'd do is you'd say, if we're just talking about functions that exist in the real xy plane. So we're not talking about complex numbers at all. Technically, you wouldn't get to that conclusion about plus or minus 6i. You'd say like, hey, there's no real solution here. And I mean real in the mathematical sense. Like you have real numbers and non-real numbers. Complex numbers being the non-real ones. So no solution on the bottom means that x squared plus 36 equals 0 at no real place. So the bottom can't be 0. So you can't have a divide by 0 error. So you can't have a discontinuity. So there's no removable or non-removable ones. That means it's a continuous everywhere type situation. Continuous everywhere. And I guess you'd have to, I haven't been distinguishing between complex numbers all that much. I'm just saying continuous everywhere, every place in the real xy plane. Let's just not read too much into that, okay? 14, it's trig time. I know you've been waiting for it. You love that trigonometry. So here it is. All right, first things first, sine. That is a continuous function everywhere. If it's just sine of x or sine of like a polynomial. Sine where its angle is not like a polynomial or a nice clean function where you can say that there's no domain issues. You gotta take into account the 16 minus x squared. So this checks out, no problem. This, we got a problem. Let's take 16 minus x squared and set it equal to 0. Well, hey, this is factorable. Look at that. So this one gives us 4 minus x equals 0. This one gives us 4 plus x equals 0. So if I just add x to both sides here, I get 4 equals x. If I subtract 4 from both sides, I get x equals negative 4. All right, so now we check this out. These are definitely places where this function does not live. And they were not obtained by like canceling something out. So they're non-removable discontinuities. And they're the only ones because sine is kind of cool everywhere else. So you'd say it's non-removably discontinuous at x equals, and you could say plus or minus 4. Now, if this were not sine, and we were talking about something like tangent, totally different scenario. Super messy. I'm not going to dig into that too much. If you want me to, send me an email and say, please show me where the tangent one is. I may or may not respond. So number 15. Oh, we got a piecewise function. looks like it's two parabolic functions, two parabolas, two quadratics. And the question is, where is this thing potentially discontinuous? So here's a way in which you can analyze it. This parabola up here is a polynomial, which means it's continuous everywhere. This is also a parabola. Also could be expanded into a polynomial, continuous everywhere. So it's continuous everywhere to the right of 3 and everywhere to the left of 3. Now what about at 3? This is where you have to show what's going on as the limit approaches it from the left. And it's called g of x. So I'll say the limit as x approaches 3 from the left of g of x versus the limit as x approaches 3 from the right. Those limits must match up in order for this thing to be continuous. And the function, it can't be an open hole there. It needs to be a hole. Well, it's not a hole. It's a point. It's a point that's, we'll take care of that. I'm getting ahead of myself. So we're analyzing it through the left limit and the right limit. Now the left, x is less than 3. We're talking about the bottom. So we just plug 3 right in. 3 plus 1 is 4. 4 squared is 16. 16 plus 1, it's 17 when you approach this function from the left of 3. From the right of 3, it's 2 times 3 squared plus 1. So order of operations says you got to square the 3 first. That's 9. 9 times 2, 18. 18 plus 1, 19. What? That's too close for comfort. Did I make a mistake? Did I write something down wrong? I did write something down wrong. This is minus 1. Should be minus 1 here. I am so sorry. Wow. Whew. Disaster averted. So you got 18 minus 7 is 17. So here's how we look at this. The limit from the left equals 17. The limit from the right equals 17. That means that if it were discontinuous, it would be a removable discontinuity. Now, if the function itself equals 17, which it does, we've got a continuous function everywhere. So the g of 3 part matches itself with the right endpoint limit because of the equal to. The equal to says, hey, you just plug it straight into this one right here. So when you have bam, 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 those 3 numbers matching up, you know you have a continuous function everywhere on the piecewise. Granted, you don't have any domain errors with the individual ones that exist other than 3, which we don't. So it's continuous everywhere. Continuous everywhere. All right, we're down to the last one, and it's a rough one because you got an absolute value bar there. X plus 3. Let's make sure I write it down correctly. All right, I got it. All right, now this is interesting because what we're doing is we're probably going to have to turn this thing into a piecewise to really give it the full treatment of analysis. So let's do that. Here's the deal. The absolute value is only encapsulating x, which means the only place the piecewise splits is at the place where the absolute value is 0. That would be x equals 0. So x equals 0 splits the piecewise. Not at 3 like we would think. 3 is not the issue. I mean, it's a domain issue, but we'll get to that. So the piecewise we have would be, let's see, from the left, you would have endpoint behavior that looks like negative x. So when you are left of 0, you would have x plus 3 over 3 minus negative x. All right, you know what? How about we just call it 3 plus x? Oh, x plus 3 over 3 plus x, it cancels. But let me just wait before I do that. From the right, it's going to be x plus 3 over 3 minus, again, it has positive x behavior to the right, so you leave it unchanged. And then you go x is greater than. Now, is 0 a domain issue? If I plugged in 0 here, and 0 here, that doesn't make a 0 on the bottom. So I would include the equal to there. Yeah. Oh boy, okay, so this requires some real analysis. This piecewise is 1. X plus 3 over x plus 3 is 1. From the left of 0. From the right of 0, you got x plus 3 over negative x plus 3, which is the same as the negative of x minus 3. Oh boy. So, discontinuities, anybody? Wow. Well, it appears like we canceled something out at negative 3 for sure. This cancellation at negative 3, at x plus 3 equals 0, that tells me we should have a removable discontinuity at x equals negative 3. And then right here, I mean, this x minus 3 down here, I don't know if you can see that very well. This x minus 3 right here, it's not canceling out with the x plus 3 on top. It is stuck, and it has an asymptote. Now, what about 0? It's just the place where the piecewise splits apart. But does it split apart at an asymptote? No, it doesn't. But here's what we should do. What you should do to test 0 is say, okay, the limit as x approaches 0 from the left is 1. The limit as x approaches 0 from the right, well, does 0 create a domain issue for this? No. You can plug it right in. 0 plus 3 over negative 0 minus 3. 3 over negative 3, that's 3 over 3, which is 1. So that means that at 0, it's continuous. But there were inherent issues with the 3 and negative 3 otherwise. All right, guys. That's it. There's limits. And academically, if you guys get all these problems done, you have successfully survived the remote learning of spring 2020. Congratulations. I'm proud of you guys for working through this. I don't think I have one person who has just straight up ignored an assignment or ignored suggested correction. So thank you. And I hope I see you guys next year without any kind of, well, let's just say adios. I'll see you next year.